So I will talk about building decarbonization with integrated simulation tools developed here at the lab. So there are various challenges we are facing with the integration of different systems and also with just decarbonization in general. So one problem we run into are competing objectives of different subsystems. So for example, if we want to reduce glare, activating a dynamic facade, we might also increase lighting demand because there's less daylight in the room. Kind of similar daylighting versus cooling demand. If you let in more daylight, there is potential for higher cooling demand from HVAC. Also for emissions, we have obviously the embedded emissions, but much more critical are the operational emissions, which are again driven on how the system is designed and especially operated as an integrated whole system, since the building is a whole integrated device. Also, let's see. We also need to provide resiliency to extreme events and survivability if there is things like a power outage. I think I mentioned before that we're typically not really designing for these type of things, but that's definitely something we should consider, especially in context of future climate change and more extreme weather events. And of course, one of the highest priorities is overall to ensure comfort, health, and indoor air quality, indoor environmental quality. But so the question is now really, how can we achieve that? And so we're working a lot on advanced control systems here at the lab. On a high level, advanced control systems basically integrate multiple subsystems of the building. So it can be, say, the dynamic facade, can be the lighting system, the HVAC system, or on-site renewables with, say, some rooftop PV, as well as also integrating with the electric power system and the availability of renewable energy from the grid, and aligning really the demand of the building with the availability of renewables. We can control the system for different objectives, which could be cost, emissions, comfort and health, or a combination of all of these. So especially comfort and health is kind of always part of the objective, but then we can weigh between cost savings versus emission savings, which may or may not be aligned, driven by the price of electricity and the dynamic emissions from the power grid. We can also provide interoperability with dynamic grid response. Again, that's related to responding to the dynamic emissions on the grid and dynamic generation of renewables on the grid from mostly PV and wind, and then scale also up into broader spectrum, such as not only one building but multiple buildings, energy communities, or like whole campuses, for example, like the whole LBNL facility here. And in order to ensure that these technologies really last for a long time, we also do a lot of work on objective modeling, which means the control system adopts itself over time and really ensures that there is a sustainable operation over the whole lifetime of the building. One technique we're using to achieve that is called model predictive control, which consists of three main components. It consists of the reduced order system models. That's a mathematical formulation of your building and the facade and the different technologies you're integrating, such as the dynamic facade, lighting, and HVAC. It also takes forecasts into account, which are weather forecasts, as well as forecasts of internal loads, occupancy, plug loads, and so on over a certain horizon, typically 24 hours. And then an optimization solver, which combines the two, so which combines the system model with the forecast and comes up with optimal set points for the different systems. We also focus a lot on having a simple configuration and simple installation so that the systems work kind of out of the box as good as possible, and as I mentioned before, over time would adopt to different use cases of the building, which is especially the case in office buildings, where the lifetime of building is, say, 50 years plus. And during these years, there can be large varieties of use cases. There are obviously various benefits we're assessing during this process, which are again related to the control objectives. So it again relates to occupant comfort, to the cost effectiveness of the technology, to the benefits of the technology, as well as the life cycle emissions. And you can see here on the right a plot where we show some incremental benefits of a technology, of different control systems or different implementation of control systems. So the first plot shows, so everything in blue is a reduction in electricity demand. Everything in red is an increase in electricity demand. And so with the first subplot, we see that basically for most of the year, we get large reductions by switching from an interior shade to electrochromic window controlled by a manufacturer typical heuristic control. So we really, by switching out the very commonly used interior shade with the electrochromics, we save a lot throughout most of the year. There are some increases during the winter period. If we now add our control system to this electrochromic window, that's the second subplot, we can see there are additional significant savings kind of throughout the year by just switching out the control system to the electrochromic window. And then the last subplot shows the integration with the HVAC system, where we can do a thing called pre-cooling, where we can precondition the building to reduce the peak demand during the day. So we see in red, we actually increase the energy consumption during the nighttime hours, where we pre-cool the building and lower the temperature, but therefore during the daytime, we have less peak electricity demand. So that's what you see in blue, the reduced energy consumption there. And in order to evaluate our tools, we need simulation tools. We can't just come up with a control system and say that's how it works and plug into a building. So we have a number of different simulation tools to evaluate these control systems. In this case, we mostly focus on the connection of two of our tools. One of them is the radiance tool, which is used to model daylighting, solar gains, and visual comfort, and then energy class for the kind of building physics simulation. And we couple these tools together in a co-simulation so we can evaluate them both at the same time. And this really gives us the ability to use the best tool suitable for the different purposes in order to evaluate the controls in the most accurate way. And that basically forms our virtual building emulator, which is illustrated here on the right. So you can see our virtual building emulator is really representing a kind of high fidelity model of a real building. So it gives a very realistic response from the simulation model. And it's then coupled with our control system, as well as with other kind of post processes, for example, to assess emissions, cost, comfort, and so on. For the IEA task 70, the lighting task we're talking about here, we're using our tools to focus on lighting, but still focus on the whole integrated building in reducing the carbon emissions and assessing them under or with the requirement of meeting all the comfort requirements which are present. I think, yep, that's it. And please let me know if you have any questions.